I'm Jared Hout.
I'm Emma Landsiedel, and this is Lab 11 on diffraction. The purpose of this experiment was to describe qualitatively how diffraction works. So we have a collimated source, an aperture here, a focusing lens, and then some sort of lens assembly, and then an observation screen in our camera. This distance is set, and this one can be changed, so we can move this to observe Fresnel and Fraunhofer diffraction. This schematic shows our known and variable distances and the distance to the Fraunhofer location.
Using these formula, we were able to calculate where the Fraunhofer region is, which is way closer than it would have been to just 22.5 centimeters due to the focusing lens. In the Fresnel region, close to the aperture, there's a low number of Fresnel zones, and as you increase the distance, the middle zone oscillates between bright and dark due to the optical path distance changing, and the number of Fresnel zones increases.
With a tall, narrow slit, the diffraction in Fraunhofer region becomes short and narrow, with the highest intensity and widest region at the center, and narrow, less intense regions to the sides, like the sinc squared function suggests.
As slit width increases, the sinc Fraunhofer pattern becomes narrower. As slit width increases, the envelope wave becomes narrower. As slit separation increases, the carrier wave becomes narrower. Those were for double slits. So for the different shapes, we have a triangle. We had different weird patterns that oscillated back and forth. For the circle, we had a target that got narrower and closer together as we increased the distance. And for Fraunhofer, we saw an airy disc with a really bright circle in the middle. And for the square, we saw a grid pattern with bright fringes at each corner. And we saw sort of a star pattern for Fraunhofer.
This is circular Fresnel as we increase distance. The purpose of Part B and C of this lab was to make sure that the mathematical models fit our actual data we collected. So the setup was the same as before, and we just took our captured images and put them into a MATLAB code to see how well they fit the data.
This is the data for the Fraunhofer diffraction that we found using the MATLAB program. For the rectangular aperture, we came up with these maxima and errors around 22 and 23% for those. And for the circular aperture, these are our maxima and worst error with 80% and 41%. But because these numbers are so small and our initial intensity was 1, the shape of the graphs was actually really close to what it should be.
This is the graph for the rectangular aperture. As you should see, it fits the sinc squared function really well. And then these lines represent the two minima and the maximum. And you can see the maximum is not equally in between the two minimum. And this is what we expect because the sinc function decays away from the maximum.
This graph represents the circular aperture, which is fit by a sombrero squared function, and you can see again the two minima and the maxima in the middle of them, although it's not right in the middle because it should decay as it goes away from the peak in a sombrero squared, just like a sinc squared. In this lab, we learned about Fresnel and Fraunhofer diffractions and how they look with different slit widths, different slit separations, and differently shaped apertures. We also learned how we can analyze them with MATLAB and fit mathematical models to them, including sinc squared and sombrero squared, and how those models do fit the curves that we get with intensity.